moving to Cisco required me to commute, which is kind of funny for people from other countries. They would say, "What? An hour? It's like 10 minutes." but for me, I didn't like it. What I've learned over the years that if you are able to explain something to someone else, then you understand it. And so I simply started making OpenGL tutorials. Why not DirectX? Simply because I was using Linux then. And so on Linux, that was the only option. So it was DirectX at work and then OpenGL at home.
Tell me a little bit about yourself and your background, and how did you get into graphics programming?
Okay. So I've been working at Intel for the past 20 years. And before that, I worked in a couple of startups. One of them was shut down, and the other one was bought by Cisco. But moving to Cisco required me to commute for a little over an hour each morning, which is kind of funny for people from other countries. They would say, "What? An hour? It's like 10 minutes." but for me, I didn't like it. So I stayed at Cisco for a little over a year, and then I moved to Intel. And so the first project that I did was on the virtualization technology, VT, if you heard about it. Back then it was a big thing. There were companies like VMware and all that kind of stuff. People were very enthusiastic about it. And however, this project, the technology I think was successful, but this specific project for Intel as a product didn't. So after almost 2 years there, they decided to shut down the project, and everybody, started searching for other stuff to do. It's very common in large companies like that. And so I heard a rumor that on the 6th floor, we were on the 2nd floor, on the 6th floor, there were a few guys who were involved in graphics. And as a gamer or ex-gamer, let's say, I played a lot when video games when I was a kid. I thought it was very cool. So me and a couple of other guys went to the manager of this team to talk to them, and he picked up all the three of us, and we started working there. And back then, the GPU of Intel, which has been an integrated GPU up until very recently, if you heard about what they call it, the ARC or something like that. I think they have, there is now a discrete GPU from Intel, which I think is very successful. I heard good things about it, but I don't have it here, unfortunately. So I use NVIDIA for some reason. But anyway, for many years, the graphics that Intel provided as part of the CPU or the SoC or whatever you want to call it was an integrated graphics. And so it wasn't good enough. And the idea of this team was to take advantage of the CPU in order to offload parts of the graphics pipeline. We'll talk about it later, but in general, the graphics pipeline includes two main stages, like the vertex shader and the fragment shader. So the idea was to take the vertex shading work, do it on the CPU, and then do the rasterization and the shading on the GPU itself. And so this was very successful, I think, for back then it was DirectX 9. So we had a bunch of DirectX games in the office that we would test and benchmark the performance and stuff like that. So it was always about performance, but not graphics. Even today, I'm still on performance. The idea of the notion of performance is very important at Intel, and you can find it in many teams.
What year was this?
This was 2007.
Okay.
And so this was when we started. This was DX9, and then we moved on. We had a few projects over the years in that team. I was on that team from 2007 to 10 years, I think. Yeah. I mean, the team changed a lot. I mean, we had several projects over the years, but until 2017, which was when I joined the current team, which involves works on performance for AI workloads, deep learning mainly. Yeah. So where were we? And so
we're talking about how you got into graphics programming. So this is, you joined the team because of the other project in the past didn't pan out, and you spent well over a decade working
on this team,
on the stuff.
Yeah, but it was never about graphics development. It was always about performance. That was the whole idea. I mean, working on the hardware in order to improve performance. So this can be like all kinds of performance optimizations and stuff like that. So the first project that we had was this one, the offload mechanism, which was part of the driver. So if you had an Intel CPU with an Intel integrated graphics and you installed the DX9 and later on the DX10 driver, then our code would kick in and improve the performance of the game. So it can be like I think it was like between a few percent up to 10-15%. But it was still considered like something that you want to do, because it's at least sometimes it would give you a few more frames per second, and people thought that it was worth it. I mean, most of the overhead is on the shading side, on the fragment shader. But in some games, there was a lot of work on the vertex shader. And in those games, when you did the load balancing between the CPU and the GPU, then you would see the benefit of our code project.
This was for the setup where you don't have a dedicated GPU.
Yeah, mostly for mobile laptops. When I say mobile, sometimes people think about Android or no, but I'm talking about laptops. Many people, a lot of students, people on the go, there are a lot of profiles of people that have a laptop and they didn't invest in some discrete GPU on their laptops, but they still want or expect to be able to play a AAA game at lower settings when they're on the train or flying or whatever. And so this was the solution that we provided them.
Okay. How did you start your YouTube channel?
Okay, so when I joined the team, there wasn't like an organized training. I mean, I think it's usually like that. You go into some team and they work on networking, okay? And so they tell you, okay, read these books or watch those videos, and you start fixing some problem, and then you understand something about, first you understand the T, and then you understand the C, and then you understand the P, and eventually you know TCP/IP, okay? Stuff like that. It's never organized. And so the same was here. There was a lot of material, but you had to figure it out yourself. And since we were working on performance, a lot of the time we didn't really understand the entire picture of how the pipeline works. Sometimes you just meddle around with some instruction or some small kernel that runs, try to measure it and try to improve to extract some cycles from it, but you don't understand the entire picture. And for me, it's always critical for me to understand the entire picture. I'm still struggling with it today on AI. Maybe we'll talk about it later. But so I decided to start learning on my own. And so the best way to learn is to teach others. If you can, what I've learned over the years, that if you are able to explain something to someone else without getting into all kinds of corners where you say, I'm not sure about this point, or this means that you don't understand it yourself. So if you can explain it fully, then you understand it. And so I started the website back. This was in 2010. I started the OGL Dev website, and I simply started making OpenGL tutorials. Why not DirectX? Simply because I was using Linux then. And so on Linux, that was the only option. So it was DirectX at work and then OpenGL at home. And so I started the website, which I think was very somewhat very successful. I think it was, because I got many messages over the years. But when you have a website, you don't really interact a lot with people, not as much as YouTube. YouTube, you can build a community on YouTube, but it's very difficult to create one on a website. And so, yeah, I continued like that for many years. And then on 2021, it was, I think. Yeah, 2021. It was back in the COVID-19 days. And I remember how it happened. I was in the living room, and I opened some drawer in the living room, and I found my wife's tripod, because she was interested in, still is interested in photography, and she had a course, a beginner's course for photography, a couple of years before that, and we bought her a simple tripod, and I just took out the tripod and I set it in the living room and put her camera on it, and then it clicked, and I had like a revelation that I need to do something on YouTube, and I always regretted that I didn't start earlier, because other people that do the same thing were way ahead of me. But that's water under the bridge. But yeah, it was that moment, setting up the camera and started talking to it. But it was still, I think it was in August. You know what? Maybe it was August 2020, and then I started the channel on March 2021. It took me a few months. I remember just starting out by watching a lot of videos about how to start a YouTube channel. And I think that many people who start on YouTube, sometimes it takes them years. I mean, they roll up this idea in their minds, and until they reach the point. This is why they always tell you, start now, start before you're ready, because you'll never be ready. You have to just start. So it was the same for me. And then it took me a few months to figure it out, what I need to do, and then I started.
Okay. Maybe we will come back to this later, in sort of like what was the impact of the YouTube channel. But I want to do the segue into the graphics itself, because a lot of people that will be listening, who might be familiar with programming. They might be technical, but graphics is sort of this weird arcane world. And to me, learning about it, how it works, opened so many cupboards in my brain, and so many things clicked. And can you lay the picture for everybody who is listening? What is graphics? What is the rendering pipeline? How this all works and connects together?
Yeah. Okay. So there were a few like major revolutions on this field of graphics. I mean, the earliest computer games, like let's say the 1980s, because the few, let's connect the end of the 70s with the beginning of with the 80s, because at the end of the 70s you already had stuff like arcade machines, with the Pac-Man and all that stuff. But everything back then was two-dimensional. Okay, and then I think it's very intuitive to understand that you have a window with so many pixels on the X and the Y. You multiply them together, you have the number of pixels that are available to you. There is there is an amount of colors that you can work with. And then if you want to create a 2D game, then there are all sorts of techniques and algorithms in order to render a sprite and to handle various cases of collision detections. And I think it's pretty intuitive. I mean, it's not so simple to implement back then because it was all assembly language, but even that was eventually moved on to C. And then I think the first major revolution was at the beginning of the 90s when Doom came out. I mean, it was in a few stages. First, you had the return to Castle Wolfenstein, and then Doom, and then Quake. And then everything, all of these came from the same company, right? ID Software. And so they were able to take the same capabilities, nothing new, except a bit more performance. There were Pentiums back then, but it was still the same technology, and then generate a 3D image. And a 3D image mainly includes perspective projection. So when stuff gets further away from the camera, it becomes smaller. And so I think that what John Carmack said, that he had a book, which I think I even have it myself here, which was a very famous book by, I think it's called, one of a few authors. One of them is Folliet and the gangs of a few other guys. And this was a university book. So it was very academic, but you could still learn it and understand the mathematics behind it. And so their breakthrough was the fact that they were able to bring it to the PC and to do it in real time. And also the idea that you can separate the game from the game engine. Because before that, most of the games, I think, were just a lump of code which would simply be good for one specific game. I mean, if you were the type of person that generates very similar games, that I'm pretty sure that you could pick some routines from a previous project and then reuse them, but there was no notion of separating of the gameplay and the logic and everything that goes into the game separated from what drives the game. And so they were able to, like creating maps and stuff like that. And then you could take the game engine, create a new map with their tools, the editor and everything else, and then create an entirely new game, which looks entirely different, but feels similar because the game engine is the same. And so that was the first major breakthrough, being able to generate a 3D image. And I'll talk about that in a second. And then the second breakthrough came at the beginning of the 2000s, I think, with the programmable pipeline. There were actually first there was the GPU. Okay, before the GPU that we have today, they had like GPUs that were able to rasterize faster. Okay, so they were able to like create lines faster on the screen or write stuff faster to the screen and then increase the performance of the game, and you could do more with that. But when the GPUs that are similar to what we have today came along, they came with a set of capabilities for like lighting the scene and doing transformations inside the GPU. So previously everything was on the CPU, but the first GPU provided you with the ability to do transformations and to do lighting on the GPU. And so it was stuff like this is how it worked for a few years, where the API was very monolithic. So what was available to you was only what was provided by the API. And then when it came to the point where people felt that it was very limited or too limited, then the idea was to simply release it release all the barriers and make it programmable. And so we switched from the fixed function pipeline to a programmable pipeline. So the idea was simply that you don't tell the hardware, this is the position of the light, this is the color, this is the angle, and you do what you need to do with it. Instead, the GPU tells you, you can write your program, you can do whatever you want in that program. I will run it for you very fast, and the result will be a color of a pixel or the movement of an object.
Yeah. Let me stop you right there so that make sure that I understand also the stages properly. In the beginning, it was just CPU.
Yeah.
And you have done everything. And this is what people sometimes refer to as like software renderer, right? It happens on the CPU. And then when people say about hardware renderer, it means it's running on GPU.
Yeah.
People realize that tasks that are needed for graphics kind of need a little bit different architecture.
Yeah.
And they separated the parts from the CPU for the GPU, and now you had like a standalone units on your motherboard, and you are outlining CPU part with the raycasting engine and its software, right? Like Wolfenstein, Quake, Wolfenstein, Doom, Quake, yeah. Then GPU with a very limited, like not programmable, so the stuff would happen on GPU, but in a very restricted and rigid way, and you needed to comply with it, and that's it.
Yeah.
Right? And then the opening up of the GPU API for programmable needs. I have a question here. Why on the CPU we start from the programmable world, and then the first GPU is not programmable? Like, to me, it kind of like, if you're doing something that you're extracting things from CPU and putting it out there, it seems like it would make more sense for it to be sort of open as well, because you start from this CPU that is a little bit open. And with GPU, it wasn't the case. Do you know why was it?
Yeah, so if you think about how the earliest CPU came along, like, for the Spectrum and the Commodore, and also the PC with the earliest Intel CPUs, they had like a single core with a set of instructions. So you had a set of instructions, you had memory, and that was basically it. And then you started writing code in assembly language, and you can create like anything, right? So you had all sorts of programs, from spreadsheets and word processing to games. People realized that they can create games even on a screen which was sometimes only white and black or green, all the oldest monochrome. And so you can write a program that would color the screen, creates all sorts of animations on the screen, load sprites from a file and put them on the screen, and then move them and create a sort of an animation, and do calculations when the sprite hits something, and do collision detection. And so all of this is like just regular programming. You have a lot of loops and decision trees and all that kind of stuff. And then when you try to create a more complex image, you end up realizing that what you're doing is running basically the same type of calculation on every pixel on the screen. It's just that the result will be a bit different because of the position of the pixel. Let's say it like that, okay? So let's say that you want to create an image as like a nested loop over the width of the image and then the height. In order to color the entire screen, you may end up running a program which is too slow because the CPU is not fast enough, and you're doing a lot of calculations, and then you start banging your head and you say, okay, I'm going to write some of this. Let's say that you started with the C language. but it doesn't work fast enough. So you say, okay, I'm going to identify the points which are very performance intensive, and I'm going to write those pieces in assembly language. And then I'm going to read like a book from Michael Abrash, the graphics programming, the Black Book of Graphics Programming, which was very popular back then. He worked with John Carmack, and he would tell you that you can use this instruction and not that one, and then you can extract another cycle, and when that cycle is for every pixel, then you can get more performance. But the idea is that you're basically running a small piece of code, which is the same piece of code on different data. Okay, sometimes it's the position of the pixel on the screen, it's something else in like the scene, but eventually it's the same thing. It's like a loop over everything, but you do the same thing. You get different results depending on all sorts of circumstances. And so people realize that what you need to do is to use maybe a different type of architecture, one which was not designed for classic programming with a lot of jumps and decision trees, how a normal program works, but simply parallel. So you can have multiple cores running the same thing. It can be smaller cores, very small cores, and have a lot of them. And they are more limited in terms of what you can do with them, but what they can do is do the sort of things that you would do in those little pieces of assembly language code that you would write in order to optimize, in order to get more performance for a game which is running on a single core CPU. And that's basically the main difference between the architecture of the CPU and the GPU. Now, eventually, when the CPUs hit some level of a frequency which they couldn't surpass because of all kinds of physical limitations, then the CPU started doing the same thing and just dividing itself into multiple cores. So you have like 8 and 16 cores on desktops today, and more on servers, even though they are still doing different work than GPUs. But for the GPUs, it was, I think, maybe guessing here a bit because I'm not too familiar with the architecture of GPUs from 20 years ago. I'm more familiar with the last 10, let's say. But I think from the earliest days, that was like the architecture. Yeah, I think it's safe to say that it was like that. And
yeah, but it started as a sort of accelerator for a very particular set of operations, and only later on was opened up to more like aspects.
Yeah, but it was not so much of the hardware as much as the software. So the software had to go a sort of evolution in order to expose the capabilities of the GPUs, because OpenGL was created in 91 or 92, something like that. Because back then there were not a lot of graphics APIs, like formal graphics APIs. So if you wanted to do something in graphics, like what the Doom guys did, what John Carmack did, you had to basically design the API yourself from the ground up. Okay, you had to be an expert on both the math of 3D graphics as well as the programming side in order to optimize it. And then you simply created everything inside the game itself. Okay, so the game would work directly with the VGA. There was you could on the DOS, back then it was the DOS operating system, the disk operating system before Windows. So you had access to the VGA. You just need to know how to program it, and it was documented. And there were a lot of tricks then that you had to master in order to get good performance from the VGA. But basically, you could do whatever you want. And in modern GPU, well, that's the main point that I'm trying to stress here, that there wasn't like a formal way. There was just the API of the VGA, and then do whatever you want with it. And so people would do different things. It was just how they thought that they should work with the VGA. And later on, at the beginning of the 90s, in parallel to what was happening on like the home side of things, you had there was a company called Silicon Graphics, which was creating high performance graphics workstations, which I'm not sure what their hardware was. I'm not sure in terms of the hardware why it was high performance. I'm not even sure if it had like what you would think of a GPU. Maybe it did for them, but it was very expensive, not available to most people. So people at home would just use the CPU, like the guys from ID Software, and then people on the corporate world that had to do stuff with graphics, like for commercial TV, and they had access to workstations like Silicon Graphics, and they defined for the first time, maybe kind of like maybe the first successful time, a graphics API for other people to use, which was OpenGL. And then suddenly you could create a program, a 3D program, without so much understanding of the GPU, but more focus on the software side of the application. Okay, so you had a certain types of capabilities. So for example, you could create a buffer and place, actually it was even before you had buffers. Okay, so the first version of OpenGL worked like that. You would specify a vertex to the program. There was an API for specifying a vertex in 3D space. Okay, and then you would write your program like that. Here's a bunch of vertices, and I'm specifying them like manually. Okay, so you can write them in some C++ array and just call the function of the vertex function on each of them. And here are the colors, and here is a matrix which will do all the math magic to make this 3D. Maybe we'll talk about it later. And then a few other stuff like lighting parameters, and then everything else was taken care of by the GPU. Okay, so you didn't have to understand whether it was VGA underneath or anything like that. So this was like a software interface for specifying 3D constructs like points, vertices, lines, triangles, with a bunch of lighting parameters and other stuff, even fog parameters.
Oh, really?
Yeah. And then the OpenGL had like a driver which would take all this information, upload it into the system. Let's say it was a GPU, then GPU, and then an image would be created on the screen. And I think there was even a version of Quake, which was called GLQuake, because eventually John Carmack had gained some access to it and understood how to use the OpenGL, and basically replaced all his rasterization routines with OpenGL calls. So all the optimizations had to move from what you would do on the VGA to what you do on top of OpenGL. And so this type of functionality was called fixed function, because you couldn't use constructs which were not defined by the API. So you had a vertex, color, texture coordinate, another texture coordinate, a few other stuff, which I can't remember, a few other attributes, and that's it. But if you wanted to add something else, then it was just not part of the API. So you're very limited. But and then the programmable pipeline came along. I think it came from probably some combination between what was happening on the academic side of things, on the research side, along with the business world. But they came to realize that what the GPU is doing when it's taking the vertices from you and it is coloring them, obviously it is running a few functions underneath the API. It's doing something with the parameters that you provided. So you can actually take this functionality and allow the programmer to write it. Okay? Because as I said, you provide a list of vertices and you provide a transformation matrix. And then the GPU multiplies all the vertices by this transformation. Why not let the programmer write a program that says, hey, this is the matrix, and here is the vertex that you created, and you define the vertex. We will not tell you anything about it. You can do whatever you want, create as many attributes. If you need 5 textual coordinates, that's fine. You need the lighting position and the world position, whatever. Here are all the attributes, and you write a program in a language which is very similar to C. It's called GLSL in OpenGL, HLSL in DirectX, but the idea is high-level shading language, and you write the code that multiplies the matrix by the vertex and send it on its way.
Maybe here we can also take a step back a little bit, because some people will be hearing like transformation matrix, and how did we come here?
Okay.
Yeah. What about like how now this algebra, linear algebra came in without like sneaking up on us? So maybe we can take a little bit of a step back and talk a little bit about the concepts from what is a 3D model, how do you get this in a 2D fashion on the screen with this process, and then maybe we can map this back into the OpenGL with its API.
Yeah, sure. So when you want to create a 3D image, which includes all sorts of objects, first you need to think about how you're going to represent the objects, okay? And so the most common way is kind of like define a set of control points. So for example, if this is the object, okay, you can see this?
Yeah.
Okay. And you want to model it into your program in some software. So you can create a set of points around here, okay, and below, and connect them in some way, like for example, triangles. You can see it. Okay. But if you think about a box, let's take a simpler example. Take a cube, a box, which has 6 faces, right? 4 around and 1 on the top and 1 below, and it has 8 vertices which define the structure. Okay, so this is all the information that you need in order to render a box and make it spin and make it look 3D. Okay, take the 8 vertices, connect them together, and create 12 triangles. And maybe I'll say why we like to use triangles. It's because it is the smallest polygon, which is entirely on the same plane. Okay?
Yeah, whatever you do to a triangle, it will remain a triangle.
Yeah, it will always be a triangle will always be on the same plane. But if you add another vertex, make it like a 4 corner, a quad, basically, then it's not guaranteed to be on the same plane. Now, having said that, it is still weird for me to think about why Blender, which is a very popular 3D modeling tool, a free modeling tool, uses quads as the basic element. But when we export stuff from, or when we import stuff from Blender into OpenGL, what we do is we triangulate all the quads. So for some reason, they work with quads, but we have the capability of triangulating those quads into triangles. And so we have the box with 8 vertices, 4 on top, 4 below, and we connect them. So we have 6 faces and 12 triangles, okay? And this is what you need in order to represent a box, just those endpoints and the connectivity information between them. And so if you want to represent a more complex image, like this guy, you just need to have more control points, right? But I think that even for this thing, you can do with like 20 or 30 control points, and then you basically have a representation of the entire object. And then it becomes more complex as the object is more complex. So if you want to model the face of a person, then you'll need something like a few thousands or tens of thousands, depending on how accurate you want your representation to be. But at the end, each model in real-time graphics is represented by a set of vertices in a 3D space and the connectivity between the vertices. So each vertex is connected to usually several vertices, other vertices, in order to create a set of triangles, which kind of like tessellate the outer figure of the model. So this is like the meat of 3D. This is where you start with. What do you do with it? You ask. Okay, so that's the next question. Like, so the 3D points, they have a value. They're represented in a 3D space. Okay, a 3D space is very intuitive because this is the space this is the world that we know. It has a width, a height, and a depth. And in mathematical terms, we know it's called X, Y, and Z. But the screen is only 2-dimensional. So how do you make it work on the screen? Okay, how do you make the image real? So here is what we have. The term is called perspective projection. As I said, stuff which is further away has to look smaller in order to make it 3D for a human which is watching it. And so you need, I think you need a piece of paper to understand it, but basically it's just a matter of dividing the X and Y by the Z. Okay? So if you think about like a triangle, imagine a triangle, and you are the viewer. You are sitting at one of the corners and looking along one of the edges towards one of the other 2 points. In order to calculate where it will be on the screen, you just need to divide this position by its Z coordinate. And this kind of like, on a nutshell, I mean, it's a bit more complex than that, and it requires a few diagrams, but I have videos on that, and it's not that not complex. It's not that complex. Basically, divide by the Z in order to project a point from 3D space to 2D. And trying to make an intuitive example for that. Like, yeah, let's take any pixel on the screen, okay, and divide it by some imaginary Z. The larger the Z, the smaller the result, right? So this will kind of like make the image smaller, okay? If you can imagine a rectangle on the screen right now. And you know the X and Y of the four corners. And now divide them by 5, by 10, by 100. The X and Y become smaller. So the rectangle becomes smaller. So that's 3D, basically. That's the entire math. On a nutshell, on one leg, as we say. On a single leg.
And often, because we shape things in triangles, if we put three things together, we have a vector. So you can describe any given transformation in a 3D space by a matrix, and then multiply vector by this matrix, and you will have another vector that will be, for example, a moved one, right? So you have a point, for example, and then you move this point X, Y, and Z to the left or to the right, or you want to scale, so make the 3D object twice as big. So you prepare a different matrix, and if you churn through all the points and multiply them by the matrix, you will have a modified 3D model. So this is a lot of like back math that is needed to handle all the transformations in 3D space.
Yeah, so the reason why we're going from, why not simply divide by Z? Okay, and so if you're writing a software rasterizer, which was basically the technology behind Doom and Quake, and if you can see just behind, you can see over there, there's this book over there, the second one from the left, that I have a video about it. It was written by Andre Lamotte, and this book came out, I think it was 2002, and this is a book about software rasterization. So no GPU, you do everything yourself, and he explains all the stuff about 3D math, and what you do there is to actually divide by the Z. So it's even before matrices. But eventually, you end up realizing that just projecting the point, so this is 3D projection, is not enough, because there are a few more transformation that you will need to do in order to actually get the image on the screen. And so it is very efficient, and I guess I would say comfortable to use linear algebra to represent a transformation that you want to do on a vertex inside as a matrix. Okay, so you have basically the three main types of movements. Let's call movement. Okay, let's spell them out and find a descriptive better descriptive word for that. You have translation, where you want to move a vertex all around, wherever. You have rotation, when you want to rotate it in a circle around a point or a vector. And you have scaling, when you want to make it larger or smaller, which is kind of like also a movement. If you think about it, scaling something up, it kind of like it moves it, basically. If it moves it from a starting position to an end position. So it's all sorts of movements that you want to do on the vertex. All of them are very simple to represent as a matrix. And there are well-known matrices for doing that. So for example, the simplest one is to scale. If you think about it, take a 3D vector, take a 3D matrix, a 3x3 matrix, which is all zeros, but one along the diagonal. And if you multiply the vector by the matrix, you get the vector back. Okay?
Nothing's changed.
Yeah. But if you change the diagonal to 2, then you're multiplying the three components of the vector by 2. So you've multiplied the entire vector by 2. So instead of simply saying, I'm going to multiply, I want to scale this image, this model. And so I want to scale it by 10. How do I do that? I'm going to go over all the vertices and just multiply them by 10. And then the entire model will be increased by a factor of 10. Instead of doing that, you can create a matrix, put 10 along the diagonal, put zeros on all the other 6 places. And this is a factor of 10 scaling matrix. But it doesn't end there. You also want to place the object in the 3D world. Okay, you've set for hours with Blender, Maya, 3ds Max, or whatever, any other modeling software, and you created a model with 1 million vertices, which looks amazing, but it is created, around like the origin of the 3D space. But in the actual game where this model will be used, you want multiple versions of the same model. Okay, it's like if it's a monster and you're going to render 1,000 monsters, then each individual monster each instance is going to be in a different location in the world. So this is another transformation for you, which is called the world transformation, moving the model or the vertex from its original position to its place in the world. So this is a translation, which is also very simpler to represent as a 3D actually a 4D matrix. Because of the translations, we're actually using 4D matrices instead of 3. So for rotations and for scaling, if what you're working with are just 3D vectors, then a 3x3 matrix is enough. But if you also want to move it, to translate it, then you have to use a 4D matrix.
And this blew my mind when I learned about it. Like that you can do this in order to still multiply matrices instead of avoiding like a plus sign and summing this up. That you can do like hack this and encode a translation vector in the 4th column. This was such a crazy thing.
I think it would best be... you can put a challenge to yourself. Take any 3D vector. Let's say you have a vector 1, 2, 3, and you want it to move to 11, 12, and 13. So just adding 10 to each component, and try to do that with a 3x3 matrix.
Yeah.
Okay, so if you want to scale it by 10, no problem. We saw this. We saw the matrix for that. But if you just want to add any number to those components, then you can do that. But this matrix will work well for only this specific vector. It will not work for all the other vertices that you have. But you want to move the entire model by 10 along the X, Y, and Z. And so this will not, you can create if you have 1 million vertices, you can create 1 million matrices, but this will not work. We want a single matrix to move all the vertices by whatever. And for that, you need to increase the number of components from 3 to 4, place 1 in the 4th component, which is W, and then it's very easy to show that you can create a 4D matrix that does that, and it's very simple. It's very simple. So this is why we're using 4D matrices. You can still provide your model in 3D space with 3D vectors, but inside the shader, you would add 1 in the W and then multiply by the 4D matrix. And so scaling, translation, and also rotation, because maybe the object is not directly in front of you. You may want to turn the monster around. You're going to hit it on its back, and so you need to rotate all the vertices of the monster around some center point. And this is also very simple to represent using a matrix. And so you have all those, and you want to do all those transformation. You want to scale the monster up or down. Maybe you have the same model, but the monsters have different sizes. Okay, so you create a different different scaling matrix for each instance of the monster, and you want to move it in the world to its proper location, and you want to rotate it, so they're not like just facing the same direction. Each one is facing a different direction. So this is rotation. And then what linear algebra provides you is the ability to combine all the three matrices together by multiplying them. You multiply the matrices together, you get some matrix which you cannot comprehend. If you just look at it, just the numbers, you don't understand why it will do what it will eventually do. But depending on the order of applying the transformations, it will do the same as applying the transformations one by one. And this is important for performance, of course, because multiplying a vector by matrix takes so many calculations, operations. And so instead of multiplying the vector by the three matrices, you just multiply it by one. So this is why we usually combine transformations together. And this is also part of what shader programming allows you to do, because you're not limited to specifying some hard-coded transformations through a fixed function API, and then it will do whatever it needs to do with it. Basically the shader is like, or the GPU is like a matrix multiplying machine. What it does best is multiplying 4D vectors by 4D matrices. That's the core of the GPU. And it's not the core of the CPU.
And I think it's useful to note that all of these transformations and computations are present in every 3D engine.
Yeah.
They're just hidden from you. They happen every time when you have a Unity and a preview window, like even in the preview window, when you have your model and you can, you have like X, Y, and Z coordinates for where it is in the map or in the scene, and you change from X0 to X6 and it suddenly moves to the right.
Mm-hmm.
Like what happens underneath is that you modified the matrix, and the matrix that is being run every frame now is different. And like my mind was blown when I realized that this is happening, because I learned this first through the engines, and then I discovered what is happening underneath, and it's like, how is this possible? How was this hidden for all this time from me? And I needed to rediscover from these like weird tutorials about OpenGL and graphics. That's wild that this can be so neatly covered and hidden from you. But on the same note, it's a bit sad that you're exposed to it so late in the process if you don't make an effort.
Yeah, so if you think about it, basically working with Unity or Unreal or whatever engine kind of like brings you back into a limited set of capabilities, because they define the interface for you. What you can do, at least on the GUI side, it's half accurate, because they also provide you with the ability to write shaders, but they need to work inside their framework. I think you're pretty free inside their framework to do whatever, but what people use who start with 3D graphics, the first few stages is like getting the correct image on the screen. So they can fail in so many places, from the way they specify the vertices, whether they upload them correctly into a vertex buffer, the transformations. They have a lot of places to fail, and it's very difficult to debug because the GPU is not as exposed as the CPU. You cannot simply place a breakpoint inside the pipeline and just debug it step by step as you can on any other program, on a normal program, CPU program. So this is usually where many beginners spend a lot of time. But if you use Unity, then it's kind of like it works, right? You open the 3D view, you have a grid, and you have a kind of like a skybox, and you have some shape or like a box or whatever they have there, and you can move it, those transformations that you said. So they already provide you with something that works, and you can modify those transformations. But it comes down to basically they take your input, create a transformation from it, and they send it inside their game engine underneath so that it will work as expected. But you can basically create the same thing in terms of the core technology of what they're doing. You can create it yourself. You cannot create as a complex software as they did, because they have hundreds of people with thousands of man years working on it. So they have a lot of capabilities, but the basic technology is something that you can create on your own with OpenGL, DirectX, or whatever.
Yeah. We stopped at the world matrix. So we went through the model, and then the model matrix, and then world matrix, and the basic transformations. So we still have a couple of steps until we have a 2D image on the screen.
Yeah.
So what happens next?
Okay. So after you've placed the images, the objects in the world, you need to place the viewer or the camera. So you place the camera in the world, and then you need to orient it in the correct direction, which is basically where the eyes of the viewer are pointing at, which means that some part of the world will be visible, like the way your eyes work, but actually most of the world will not be visible because it will be too much to the side or up or exactly behind you. And so you understand that there is some limit or extent to what you can see, and we call this the view frustum. Because if you try to define what is the limit to your actual eyes, it's kind of like weird. I mean, it's like it's a rounded shape, right? Our eyes are round, and then you can kind of like see it round on the side and over there, and from there it's kind of like something like that. And it's not very friendly to computers. And we have a rectangle window. So what we do is to use a chopped off pyramid, which is called the view frustum. So you take a 4D pyramid, a pyramid with a rectangle on the bottom, and there is a top, and you chop it off to have rectangle on the far side and rectangle on the near side. Yeah, and then this is what limits your view of the world. And then you say, okay, no problem. What's inside can be viewed, what's outside cannot be viewed. And let's now use the trick with the division by Z in order to project the object on the screen, which is kind of like, let's say, the near side. So it's a bit more complex, because the way that the camera is oriented, it may be like tilted or like that. You're looking up, you're looking down. The math, if you try it like that, the math will be very difficult. You can do that, but it's very difficult. So people realize that the math will become much simpler if they can get the world to look as if the camera is always pointing along the Z direction, and the camera is always located in the origin. Okay, on the 0, 0, 0 location. Move the camera to the 0, 0, 0 location, the origin of the 3D world, and rotate it so it is upright, okay, pointing like the head points directly up along the y-axis. You're looking straight ahead, and the direction is the z-axis. Whether it is the positive z or the negative z is a different story, but if you do that, then all the 3D projection becomes very simple at this point, and then it is really division by z once we're at this orientation. And so to do that, it basically means move like the entire world along with the camera. Okay, so there is some orientation, some relationship between you and the object. Okay, if the object is right behind you, or let's just in front of you. It's simpler to think about it. Just in front of you, and it is like 10 meters in front of you. But the camera is located at location 100 on the x-axis, okay? 100 on the x and 100 and 0, 0 on the y and z. So let's move the camera by minus 100, which will move it to the 0. And then everything else also needs to move by minus 100 on their respective axis, okay? So this is the first transformation. What we're doing right now is moving from the world space to a view space. The view space is when the camera is at the origin looking along the z-axis. So first of all, we calculate the transformation to move the camera to the origin, which is actually very simple, because if the camera is at some x, y, and z, then you simply translate it by minus x, minus y, minus z. And when you apply that to x, y, and z, you get 0. So the camera is moved to the origin. You apply the same transformation on all the objects, and now they have moved like whatever, but the world seems like it is the same. The orientation between the camera and all the other objects, it seems like they've never moved. Okay, it's the same thing. And then what you do is you handle the looking at along the z direction. You calculate a rotation to the camera to fix all those changing along, moving the head to point to a different location. You apply a rotation so that the camera is looking straight ahead along the z, and then the camera is rotated to that, and then you apply the same rotation to all the other objects. So if something was in front of the just in front of the camera, but the camera was not pointing along the z direction, now when you rotate the camera, this object will end up, if you do the calculation correctly, this object will end up sitting on the z-axis, right? Because the camera is looking at the z, and the camera was previously pointing at this object, so it still needs to point to the object. So this rotation will take the object directly to the z-axis. That's the idea. So this is like rotating the entire world around the camera to follow the change in direction of the camera to the z-axis. And now we are in view space. Basically nothing has changed, but now everything is set up much easier to do a projection. And the reason is that if you try to do projection inside world space without all this hoopla of the camera, then you will need a different projection matrix for each position and orientation of the camera. But moving everything like that means that you can use the same projection matrix for whatever position and orientation of the camera. You've separated the two stages together, and then in many cases you will see that the projection matrix is calculated once at the beginning, and then you don't need to change it. And so now, after moving to view space, we do projection, which will project the points to 3D to a 2D space. We kind of like divide by Z. There are a few other stuff there. The projection matrix includes or also handles stuff like transforming the Z coordinate, because when you define a camera, what we usually do is to define a near and far Z, like the closest Z position which is visible. It's like if it's too close to your eye, then it will be clipped. If you're like standing next to a wall and it is too close to you, you can actually, it might be clipped away. It's sometimes a problem when you can see in all kinds of games. But the idea is that you don't see everything from like position 0. Usually it's a bit further away. And then there is also a far Z, which defines the end of what you can see. And actually making them close together even helps you increase or helps you get over all sorts of anomalies. One of the anomalies which is very common is called Z-fighting. If you take two objects and you have very close Z values, when you rasterize them, they look like they are interlaced. Because of numerical issues, this tends to happen. So one of the fixes for that would be to use a smaller Z range. And this is also part of the projection matrix. The projection matrix is also takes care of the aspect ratio, because rarely the window is a square. It is usually a rectangle. And so you can actually see like more on between the left and right than from the top and bottom. So these are like the three major responsibilities or capabilities of the projection matrix. Everything is like pushed into this, lumped together into the same matrix. The projection, or at least half of the projection, to be honest, and the aspect ratio and handling the Z range. But there is a problem with linear algebra. We said that you need to divide by Z, right? But actually, you cannot really divide using a matrix. And so what we do, the projection matrix copies the Z value from the Z coordinate into the W coordinate. And then the hardware has a fixed function stage which divides by the W, which is actually the Z. Oh, this is called perspective division.
This is like a fixed function on hardware.
Yeah. So the GPU is not entirely programmable. It has programmable stages, which we may want to go over them also if you want to like complete the picture of what is the programmable pipeline, how everything works. But the idea is that you have programmable stages where you can plug programs into, and they will be executed by the GPU. They will be written by GLSL, which, as I said, is very similar to C language, but it also contains fixed function operations. So the major fixed function stage is the rasterizer, which takes the points that are coming out of the vertex shader and finds all the three points which represent a triangle. You need to find all the points inside and then execute the fragment shader. So this is what is called rasterization. The rasterization is still a fixed function mechanism. So in addition to that, and of course in modern version of OpenGL and DirectX, you also have the tessellator, which also includes programmable stages and the fixed function stage. So I think from an architecture point of view, what they did, the designers of the hardware and the software APIs, they identified the places which should be programmable, as well as stuff which is still better executed as a fixed function hardware. Because when you have a fixed function hardware, which is good for one thing, you can create a smaller mechanism or device inside the entire GPU to take care of that, compared to like a programmable part which knows how to execute instructions, and it's very complex. And so what we have after the vertex shader, you multiply by the projection matrix, which is set up in a way which is ready for perspective division. And then after the vertex shader, a certain type of variable inside the shader, an output variable from the vertex shader called GL_position. It's a 4D vector. The hardware will divide by its W component.
I didn't realize that.
Yeah.
I always thought that it's gonna be just passed further along.
Mm-hmm. Yeah. And because because it divides by the W, and you know that you have to divide by Z from a mathematical point of view, what your projection matrix needs to do is to move or copy the Z to the W. And so when you divide by W, you divide X and Y by the Z. So everything was, it's not by chance. Everything was designed like that from the beginning. So they kind of like, they are funneling you towards a certain type of behavior. If you don't follow correctly, then you will end up with a black screen. So you need to have all the transformation correctly.
And this is very much different from CPU style of programming, where you're kind of free to do whatever, right? Like here you have a set of things that should happen, and only in this programmable stages you can actually influence things so that you have maybe some style of rendering, right?
Mm-hmm. Yeah.
We talked about the math, how to adapt your vertices so that they are there, but we didn't really talk about shaders.
Mm-hmm. Yeah.
And how this looks like from your from scratch C++ stuff, because we talked about loading the model. You have a model, you have 3D information, and you provide these, you create these matrices that will be then happening on vertex shader. But we didn't talk a lot about shaders themselves, how they happen, because you also need to set them up. So maybe we can spend some time discussing that.
Sure. So if you've created a model inside the 3D modeling software, Blender, Maya, whatever, you export it to a file, and then you have a file which contains all the information about the model, the vertices, the connectivity of the vertices to triangles, and all the additional information such as texture coordinates, colors, textures, whatever. Texture coordinates and textures, okay, those are different, of course. Textures are the actual image which provides the color of the triangle. So if you think about the original simple example of the box, you want to put some texture there, then you have some image. But in order to render it correctly, the vertex needs to know how to map into the image. So in the case of the box, let's say you want to place the entire image directly on the box, whatever the size of the box is, then you provide textual coordinates to each vertex that go from like 0, 0 to 1 by 1 on the other side of the face. And then this basically tells us to put the entire image. Okay, so textual coordinates are represent the position of the vertex inside the image, going from 0, 0 on the bottom left to 1 by 1 on the top right. And so all this information is now sitting in a file. Your OpenGL application loads the file, parses everything, and then creates a buffer with all the information. Okay, so you create a GPU buffer, kind of like a GPU vertex buffer, which will eventually go into the GPU. The system will take care of moving the information from CPU memory, where the loaded file is, into the GPU later on. Let's say that this is a discrete GPU that has like 8, 12, 16 gigabytes. You want to run everything from the GPU. So the system will take care of that. And what you need to do is to lay out to provide the format or the layout of the vertex. So you need to say my position, the position of the vertex in my vertex, the position of the vertex is at the first 4 floating points, or 3, actually 3. And then we have a textual coordinate and then color or whatever. But you can also change the order. Let's say that you want the color to come first for some reason. You can do that. And OpenGL gives you, just a second, gives you the ability to specify different locations. So this is all free for you to decide. You can even separate the attributes into different buffers, which is called AOS versus SOA. AOS is array of structures versus structure of arrays. So you can place all the positions in one buffer, and then the textual coordinates in another buffer, and then the colors in a third buffer. So you can do that as well. And this defines the structure of the vertex to OpenGL. And then what you need to do is to write a program in GLSL, the high-level shading language, which takes this vertex and do some transformation with it. So you can think about the GPU as kind of like a factory, the idea of a factory where you have different stages, like an auto factory. They start with, I don't know how they create automobiles, but they start with something inside the very structure. You have a stage that does that, and then it moves to the next stage, and they put something on top of that, and eventually they put on the wheels, and at the end of the factory it goes out and it is ready. So on every stage they do the same thing on the incoming input, and they output something else. So it's kind of like the same with the GPU. You have vertices. You can have a single vertex or a million vertices. It doesn't matter. And you have a kernel, which is this program. This is what we call the kernel or a shader program, which will be executed on every vertex. So this is the first stage in the pipeline, executing the vertex shader on every vertex. And one of the characteristics of the vertex shader is that it cannot create new vertices, and it cannot drop a vertex. So let's say your program says, I want to get rid of this vertex. I don't like it for whatever reason. It doesn't work for me. It cannot get rid of it. Okay, this is some of the limitations of how the system works. Single input, single output. And so the way that the structure of the vertex looks like is that you define the input attributes of the vertex. You have position, which can also be 2D. If you're doing something with 2D, for example, you can define a 2D vector as a position. You don't need the Z for whatever reason. So you're free here again. You can have a position which is 2D, 3D, 4D, whatever. texture coordinates, colors, everything else. These are your inputs. And so the system, for each execution of the vertex shader, will plug in a different vertex, the next one. Okay, so it goes over all the vertices in your vertex buffer, takes the data from the current vertex, puts it into the vertex shader, and then execute the code on this data. And so this is how it looks like. You have like kind of like global variable. People coming from C are sometimes feel they are a bit mystified by it because it looks like global information, but in fact on every execution of the vertex shader you will get a different vertex there, so you have a different data. And then it executes the vertex shader, which is just some kind of a C code. In addition to the input attributes, you also add uniform variables. So like all the matrices that we talked about, you plug them into uniform variables. The difference between a uniform variable and the vertex attributes is that the vertex attribute changes from one vertex to the next, but the uniform stays the same throughout the entire, what we call a draw call. In order to execute this entire machine, you put out a call to GL draw arrays, GL draw elements, or any other few types of OpenGL function calls. You tell it, I'm gonna refer to this information as points or lines or triangles, depending on what your modeling software created. And I want to execute from this vertex from 0 to million, from 5,000 to 6,000, whatever number of vertices you want to execute, and from whatever offset, you can do that. And once you do that, the system takes over and it will execute the vertex shader for you on the specified vertices. And so what you do in the main body of code in the vertex shader is the transformation. Takes the matrices from the uniform variables, multiply them. They can include, usually the vertex shader is responsible for like moving all the movement and rotation and scaling of the object, but also on stuff that prepares it for like shadow mapping. The way that I'll just say one word about it because it's an entire topic by itself. But when you want to create a shadow, it means that you need to render the scene from both the camera point of view, which is like the default point of view, but also from the point of view of the light. So to do that, you need to provide yet another transformation matrix, which is kind of like placing the camera at the position of the light. And then you will multiply the same vertex by the two matrices. One will be used as like the regular transformed vertex for the continuation of the pipeline, and another will make it look like as if the camera is actually at the position of the light. Okay, and then you have...
That's so cool.
Yeah, you have like a regular position, which you will use for rendering, but also a light position in order to render it correctly into the shadow map, which will later on be used in order to identify whether the pixel is in shadow or light. So all this stuff is classic vertex shader work, but it's actually very limited compared to the fragment shader, which we will get to in a minute, which is why vertex shaders are usually shorter, because there's not so much that you can do with them. What we usually do in vertex shaders also is to take care of skeletal animation. Okay, we haven't talked about animation, but what you can do with modeling software is to create a model of something which needs to move, like a person or a monster or whatever, or robot. And then you start moving the arms and the legs, and you record different locations in time, like your hand moves like that and like that and like that, and you record the transformations for those a few stages along the way, and then you can do like a smooth movement of the hand. This is called skeletal animation. It's a bunch of transformation. It generates a bunch of transformations on its own, usually provided also to the vertex shader. So these transformations are also the responsibility of the vertex shader. Sorry.
So the animations are not done just by changing the model matrix of a given part, like bone.
Yeah, so regular movement, I mean, you can, if you just want to move the box from one place to another, what you would do is to change the transformation matrix, like the position, slightly on each frame, and then it will be rendered in a different location. And if you make sure it is smooth enough, you match it to the frame rate, it will look like it is moving. So this is animation. This is the very simplest animation that you can think of. Skeletal animation is when inside not the box, because the box is too limited, but inside the body of a person, you identify the main bones, and you move them in a way which will look believable to you as the person who is doing the modeling, and you will record key locations along the movement. So if you think about, you want to make it like it's walking, you can create, like an artist can create a set of 10, 20 images of the legs in different positions. And if you just look at the images, you will see that what he's doing is create mimicking an animation. Okay, so you can do it by hand with a pencil, with a pen or pencil on a piece of paper, and you can also do it inside the modeling software. Just the mechanics are a bit more complex, but what you will end up is with a set of locations and rotations for each joint and each bone. And so all this information is also outputted into the file of the model, and can be loaded. And then you can generate what you usually need to do is to create to interpolate between the different locations based on the point in time. Okay, so if your game is running at a faster frame rate, 60 FPS, 100 and 120, the faster it goes, you will create more key points between the different transformations. If it's going, if the game is running on a weaker machine like 30 FPS, then the distances will be greater. But all this interpolation needs to happen. It is the responsibility of the application. But eventually, it's just another set of transformation matrices which are provided to the vertex shader. And the vertex shader, again, will need to multiply. Usually what happens is that on each point in the body is usually affected by more than one bone. So if you think about an area in your hand which is exactly between the two joints, then like between the hand and the elbow, then you would say that this point will only be affected by the movement of the hand. But if you have something which is like here, in order to make this believable, you would want this point to be affected by both the hand and this part. Otherwise, it will look like a robot, and you want to make it smooth. Then this is another thing which is calculated by the modeling software, that it gives what is called a different weight to each bone. So each pixel can be affected by multiple, or vertex can be affected by multiple bones with a different weight to each one. And so what the vertex shader needs to do is to get all those matrices and to do an average of the different matrices. So you have one matrix which you multiply and give it like 80%, and then a different matrix will only affect by 20%. Okay, again, classical vertex shader stuff. And so, okay, so you do all those transformations, and you output some of the or all of the input attributes out. Sometimes you can simply move them along unchanged, but sometimes you may want to apply some calculation on them. So for example, if you have a texture coordinate, you may want to multiply it by a value in order to stretch the texture or make it more dense. So this is also a type of calculation which the vertex shader does, and then you output the texture coordinate, the colors out as an output attribute. So you have an input attribute and an output attribute, and the minimum you need to do is to copy from the input to the output. But in many cases, you will also do some transformation on the data. But the most important thing is the position, right? Because you want to see it. And so, as I said before, you have a dedicated like system variable, which is called GL position, that you need to put the position there. Okay, so you have an input position, you have all the sorts of all matrices, few matrices, you do some calculation, and the result eventually needs to go into the GL position, because this is what is going to be used for rasterization. And this is what will be used for the perspective division. So it's very important to write the position, the final position, into the GL position, which is a 4D vector. And then you have perspective division. And then we get to the rasterizer, and the first thing we do kind of like is the clipping, because basically what we did in the vertex shader is that we applied all the transformations to all the vertices, but of course some of the models were behind you. Okay, so the clipper clips the image to be between minus W and W along the X, Y, and Z components. And it's a bit more complex, but this will eventually throw out everything which is too much to the side or behind you or too further away. And then we will basically take the coordinates and map them to the screen. And now the rasterizer can start working. It ran the vertex shader on the position of 3 corners of a triangle. It can now identify all the pixels inside this triangle. It interpolates, okay, along the face of the triangle. And what it does next is to execute a fragment shader, because basically now we know which pixel is going to be visible, but we don't know the color. The job of the fragment shader is to calculate the color, the final color, which will go on screen. And this is where most of the work takes place, because of the algorithms which are becoming more and more complex. So initially, up until, I don't know, maybe 10 years ago, 15 years ago, you had very simple lighting models. So what is known as the Fung model. You have an ambient and diffuse and specular light. An ambient is like just apply you have a color of the light, and regardless of the position, it's like the sunlight without thinking about the position of the sun. You have light all over, right? You can kind of like model it by giving it some value and then applying it on a pixel. And this is ambient light. And then you have diffuse light, where you take into consideration the angle between the ray of light and the position of the face of the triangle. So you need to do some calculation there. If it's pointing directly at the triangle, then it is on the maximum level or effect of the light. If it's more like to the side, then it becomes weaker and weaker. And then specular, which is for stuff which is sparkling or flashy. And this is one type of calculations which goes into the fragment shader. But this is a very simple lighting model. Today we have physically based rendering, which is way more complex. So this is all of these calculations needs to go into the fragment shader. Also, you may have multiple lights. What do you do then? You need to basically sum them up. So you need to provide all the lighting information to the fragment shader and sum up all the effects from all the lights until you get a single value. So usually the output from the fragment shader is very simple. It's just the color of the light.
Color of the pixel.
Color of the pixel, or fragment as they call it in OpenGL world. Fragment shader. Pixel shader in DirectX, but it's actually a pixel.
What is the difference? I knew this, but I forgot. What's the difference between fragment and pixel in OpenGL?
Well, in OpenGL, they don't talk about the pixel, and fragment is kind of like, I don't know, an atom or whatever. I don't know why they call it. But I think that Microsoft came later and they needed to change it to have a different name. So they said, well, fragment, you know what? Pixel. We're gonna go with pixel. Yeah, it's free for us.
Okay. Mm-hmm. Now, if you look at the OpenGL API and you sum up all the stuff that we're doing, we were doing things like generate buffer, so reserve some memory, right? And then GL vertex attrib pointer, which is like defining the layout for the vertex. Bind some buffers, create program, use program, couple of calls for drawing. If I were to sum up, it's probably like 20 to 40 function calls, right? And this I can wrap my head around. But OpenGL spec has like 800 functions.
Yeah.
What is happening in those other like 750 something?
Yeah, I think functions? That many of them are not really used. And first of all, you have a lot of variations. So for example, just to execute a draw call, as I said, the basic tools are GL draw arrays, when you simply have a set of vertices in a single buffer. And you each, like the first three are a triangle, the next three are another triangle, and so on. But you also have index draws, where you have kind of like a redirection. You have an index buffer, and each index points to a vertex, and then if you want to share vertices between triangles, you can simply reuse the same index. So that's GL draw elements. But also you have instancing, where you render the same vertex buffer with different with changing attributes or changing matrices. Instead of multiple draw calls and changing some matrices between draw calls, you can do a single draw call with all the matrices, all the different matrices in yet another vertex buffer, and then tell the system to render 1,000 instances, which will work faster because it's all wrapped in a single draw operation. Often you would see that in OpenGL optimizations, they try to decrease the number of draw calls because usually the OpenGL drivers are very big and complex, and they incur a lot of overhead on the CPU. And so optimize with OpenGL is to try to minimize the number of OpenGL calls, and they help you in some respects by providing you with APIs that do more or hide some of the loops inside them. Instead of doing a loop on the application side, they do the loop for you and change and tweak stuff in between according to the specification. And so we have multiple draw calls, and there's also a lot of explanations there about the way it works, the way it should work, and so not everything is just specification of functions, but I think you end up with a few more than 20, 40. I need to count the number of OpenGL calls in my tutorials, and then I can tell you if it's. But it's not a lot. It's true. It's not a lot. And
it's not like there's like a lot more functionality to it, right? Like in terms of what OpenGL provides as an API.
No.
It's just that you can do more in terms of math, but within the same functions. For example, to do like more sophisticated shadows or lighting or something like that. Is this correct?
Yeah,
like
I mean, everything eventually is in the shaders, and the shaders have their own. GLSL has its own specification, which is not part of the OpenGL specification. So you can actually do very well without reading the entire OpenGL spec once, or even parts of it. I mean, you don't really need to go to the spec a lot. You can get by with just reading the man pages of the functions. So the specification is more for the hardware developers, the people who are writing the drivers, and they need to adhere to a specification so that each OpenGL application will hopefully work the same on each platform, which is rarely the case. But it includes all the different error codes for each function and what it needs to, where do errors happen, why do they happen, where and when should they be triggered. So it's also part of the spec. But yeah, it's big.
When you said about minimizing draw calls, this is true for every graphics API, right? This is not only for OpenGL.
Yeah.
So each driver will have the same sort of issue, that the less draw calls you can issue with the data already being there in GPU, the faster will be your program in general.
Yeah. So if you have the same, basically this two different implementations of like the same algorithm, but one has half the number of OpenGL calls, then it has a greater chance of running faster than its counterpart. Again, depending on how much overhead, if this is a very efficient driver, then you may not notice it. But usually you try to reduce the number of draw calls. And this is one of the reasons why Vulkan came along.
And this is why I wanted to ask, like, is there something on the OpenGL that we skipped before we enter the Vulkan world? But I think we wrap the OpenGL part and
I think
start talking about Vulkan.
Pretty much covered most of the interesting stuff. Yeah.
Okay, so tell me about Vulkan. Tell me why this API is, I wouldn't say hated, but it's complex, and the complexity is quite visible.
Yeah.
And a lot of like internet voices would be sort of flooded with the complexity a little bit, like annoyed and vocal about it. So why OpenGL was limiting to the point where Vulkan came along? And because for everybody who is listening, Vulkan is being created by Kronos Group, which is the same group that was doing OpenGL. So OpenGL is discontinued now. It still works, but the Vulkan is the main place where innovation happens and things are being added. So what Vulkan brings to the picture.
Yeah, so let's say that you start learning OpenGL, you set up the basic window, and then you create your first render loop. Okay, the main loop which generates the frame. And so the first thing you do is you put a clear operation. Okay, so you clear the window to some color, and then you start adding stuff. You have your first draw call. Okay, you render your first triangle. You need to bind. You need to bind a vertex buffer, and so basically, if you have just a single vertex buffer in your program, you can actually bind it outside of the render loop. But let's say that you have a few vertex buffers for whatever reason, vertex buffers. You bind one buffer, you issue a draw call, you bind another buffer, you issue another render draw call, and so on. You get to quite a few draw calls eventually, because the image becomes more and more complex. And then you have textures. Of course, you have different textures. All of your models have a lot of textures. So in addition to binding the vertex buffer, you also need to change between textures. So you do that as well. And you end up with kind of like a recipe of changing all the state and issuing draw calls. And you also change stuff like, in some cases, you want to enable or disable the depth test. You want to change culling, you change blending. There's tons of other stuff which is not draw calls and is not buffers and textures, all kinds of knobs that you can play with, and you change them as well. And then you say, okay, but what I'm actually doing is I'm running the same recipe, the same procedure, the same sequence of operations, and what I'm actually changes is just a bunch of matrices, because it's always for this set of draw calls, it's always this set of textures, the same textures all the time. It's the same model, and I'm just changing the matrices. So what if I can create some mechanism, a command buffer, let's call it, which is what is actually the actual name in Vulkan. Let's create a command buffer which is going to wrap all of the state changes and draw calls that we know that we need to do, and we're going to record them. All the operations we're going to all the commands we're going to record them into a command buffer, and then we'll issue this command buffer, and then just change the matrices. We'll provide the user with some mechanism that will allow him to update the matrices in each frame, because this is really the dynamic data which you cannot predict. But you can predict, as a developer of the game engine, you know exactly what you're going to do, so you can record it beforehand, and then you just submit those command buffers, and then those command buffers will include all the information that they need. They will already be baked into the layout that the GPU expects in terms of the communication between the driver and the GPU. And then that's basically Vulkan. That's the whole idea of doing stuff beforehand, and then doing as little stuff as possible during runtime. Everything is already ready for you by the time you get to the render loop. Kind of like it's a bit more. It's never that easy. It's never like zero work. It's not zero work, because you still have lots of dynamic decisions that you need to make. Like, for example, if you do culling, if you identify that some object is entirely out of the visible area of the camera, then you want to drop it and not provide it to the GPU at all. So this is one of the calculations that you may want to do, and then decide whether to submit this command buffer. So it's not like you can create one command, unless it is a very simple application. It's not going to be just a single command buffer, but a few command buffers are going to wrap like, I don't know, 80-90% of what was previously done by a few hundreds of OpenGL calls. And then you just need to submit it.
But you still have a lot of initialization work, like on swap chain. What is a swap chain?
So back then, if you go back to the software rasterization days, the way that the VGA worked is that it would literally scan the entire window from like top left to bottom right. It would do that like 60 times per second, and then it would take the information from some memory buffer, the color, and then put the color on the screen. And then if you change the image while it is scanning, then you would see some kind of a nasty flicker. And so what they did, that they identified, I forgot the name, retrace or vertical retrace or something like that. The little pause that there is between getting from to the end to the bottom right, the ray needs to go back to the beginning. There is a little pause there. So if you change the pointer for the rasterization, for the presentation engine, you change it to point to a different image, then it will start on that image. And then if you don't touch it while it is scanning, then the image will be stable. Okay, so what you do is double buffering. You modify one image, the back buffer, while its brother sibling is being displayed. And then when the presentation engine, the ray goes back to the beginning, you flip the buffers. And then front becomes back becomes front, and then the new one is being displayed, and the next one is being rasterized. So this was the case in very old TVs from like the 80s and the 90s. And today, I think that today's technology is not like that. But the notion still exists there in terms of, so I think that if you would work with a single buffer, you will still end up with the same problem, but it's just the technology is not like, there is no tube today. Back then, you have the large TVs. There was actually, at the back of the TV, there was a ray that was scanning the image 24 times per second or whatever. And so the technology is different, but the problem remains the same, I think, even with the newer technology, which is why we have the notion of a swap chain, which contains several, at least two images for doing double buffering. This is true for both OpenGL and Vulkan. In Vulkan, the swap chain is an actual object. So this is something that you need to create and manage, because another thing in Vulkan is moving the work and most of the responsibility from the driver to the user, to the developer. Because one of the things that we had to do back then in the DX9 and 10 days was to try to understand what the software is trying to do and maybe help it by optimizing things underneath. But the software is not really providing you with hints. So even though you're running the same render loop each time, as a GPU, as a driver, you have no idea that this is what is going to happen. You don't have access to like the code. You're not going to analyze the code and say, okay, I know that the next frame is going to be the same, except that some matrix is going to be different. So I'm gonna skip some of the stuff. No, you have to be ready for any change in any state, even though it's not going to happen. So the driver includes a lot of error checkings, and a lot of management of command buffers, because actually command buffers do exist in OpenGL and DirectX, but not as part of the API. This is usually how the software talks to the GPU. It actually creates command buffers and fills them up with information and provides them to the GPU.
Okay, but then
they simply
is
exposed it to the developer.
Okay, but what is it there to for example modify in swap chain? Like you can create it, you can set it to for double buffering, and then what? Like what's there to manage?
Yeah, you can control the number of images. You can decide whether to use 1, 2, or 3 images. More theoretically possible, but there is a problem with creating too many images because there may be some disconnect between what the player is doing and what they're seeing if you have too many images, because you're already running too fast into the future if you're creating more images. So 2 or 3 buffers are probably the maximum. The swap chain also includes information such as format and whether it includes depth buffer. So there's a few pieces of information, and they decided to expose it. Also, different presentation methods. So for example, they have FIFO and mailbox and few different ways of replacing an image. So for example, in one method, it will simply traverse in a loop over all the images. In another method, if a new image comes along, it can override an existing image which was not yet being rendered. Okay, so if there is an image in the queue, but another one came along, and the presentation engine hasn't been able to render the waiting image, it can replace it with a newer version. So there are a few capabilities there and some improvements.
Okay. And some other ways or new capabilities that Vulkan provides is, for example, the idea that you can have a much more programmable stages in terms of you can define what you have in terms of shaders one after another.
No, it's actually the same shaders. So Vulkan provides a vertex shader, geometry shader, tessellation shaders. Okay. Yeah, in terms of the shaders, you have the same stages. It's all a management of. Okay, another feature. Vulkan is mostly for performance. The guys who are responsible for in Kronos, who are the designers of OpenGL, they've been researching it for years. They identified all the bottlenecks, and one of the bottlenecks is that OpenGL is very limited in terms of multi-processing or multi-core on the CPU. So it's difficult to render. What happens when you submit draw calls from different threads? It's not so well defined. Usually you have a single rendering thread which takes all the rendering work, and then if you want to offload some of the stuff to other threads, you can do that as long as you don't do changes to the actual OpenGL work. So they opened it up entirely in Vulkan. They allow you to submit command buffers from different threads, place synchronization mechanisms directly into the command buffer. So you can say that, hey, this command buffer is going to be dependent on this one and will be executed after that. And if your application is one which does record command buffers during real time, which is kind of like I think not what the purpose of command the whole idea is to record them beforehand and then submit them. But if you want to record them, you can create command buffer pools on different threads, and then each thread will have its own pool to record command buffers from.
Okay.
So you don't create, you don't allocate a command buffer out of thin air like when you call malloc. You have to create a pool, and then you can allocate from the pool, and you can return stuff from the pool, which is often what you do when you want to reuse a lot of the same memory, even for any other type of software, right? You create like pools of objects, and then you allocate and deallocate. And so it's the same in Vulkan, only that they allow you to create a dedicated command buffer pool for different threads, and then the threads will be entirely independent.
Okay. So if you were to compare a Vulkan and OpenGL, what would be the dimensions and differences?
So there's a lot more responsibility on the developer. I think that Vulkan is a much bigger challenge, especially for beginners. And in many cases, there is a trade-off, because you're gonna spend more time on debugging. You may end up not having enough time to do kind of like interesting work. You want to implement a more sophisticated lighting model, but you end up not having enough time because you need to set up the framework or the game engine working correctly, and it takes a lot of time with Vulkan, because everything which was offloaded to you, the developer, as well as error checking, stuff which doesn't work correctly. Previously, you could get a hint from the OpenGL driver, or the driver would make sure that you will not crash. With Vulkan, it would crash more often, even though you do have validation layers which are pretty good. Actually, they did provide validation layers to Vulkan, which can be enabled or disabled entirely, so you will not have any overhead from error checking, only during development, and they will test and trigger any fault that you make in terms of not adhering to the specification. So this is good, but a lot of responsibility moves over to you. And so this is something that you need to be aware of. And in many cases, you may not need this improved performance. I mean, there's always a question of whether you need to actually develop the game or whatever using OpenGL, or simply use a game engine. I think that most games today are being programmed with game engines, right? So
yeah. And also, like, if you decide to go with Vulkan, then you take more complexity, as you mentioned. You will need to spend more time on setting this up and making sure it will work. And the performance gains only make sense if your game would be bottlenecked on the GPU, right? And it's
also
not necessarily the case.
Because Vulkan does allow you to make a better use of the CPU as well.
Okay.
Multiple rendering threads, and so if the type of workload that you're going to create runs fast enough with OpenGL, then why go to Vulkan?
Yeah, it might be also tricky to tell in advance, especially if we're talking about like AAA games. We're doing things from scratch with a custom engine, and like you don't really know what will happen in 3 years when the full game is out there. Okay, now if you remember in the beginning when we talked about your YouTube channel, we said, let's talk about OpenGL, and then we come back. Now, after like 2 hours of discussion, we come back. When you make videos for OpenGL and Vulkan, what's the difference in the response of the audience? What is more preferable? What is how people react to these videos, and how is it different to make videos for OpenGL and Vulkan?
So OpenGL usually gets more views.
Okay.
Yeah. So I think that people, or at least, you know, in terms of the material, because it's a bit of a different material. I made a kind of like a business decision to focus on graphics and math and techniques and algorithms on the OpenGL series, and on the Vulkan series focus on the API. So for example, right now I'm working on physically based, I'm using some book which I've recommended, which is the 3D rendering cookbook. The first version was OpenGL and Vulkan, and the second version is only Vulkan. And so I'm still using both of them because the first one supports OpenGL, and I'm taking stuff for OpenGL from there. But even on the second book, for example, if they explain the physically based rendering, what I'm going to do is to present. I have a previous video on physically based rendering, but this is like more advanced using GLTF2. So I'm going to present it using OpenGL, and then just take the shaders to Vulkan when the time comes and just show the integration. So this is kind of like in Vulkan, focus on the how to use the API correctly. On OpenGL, there, as you said, there is not so much of an API. You learn how to create the buffers, load the textures, and from now on, it's a lot of shader work and framework. So for example, if you need to create a render pass, if you need to render into an off-screen buffer and then read from me, then you need to call the OpenGL functions correctly, but 90% of the time it's shader work. And so if I present all the algorithms if I explain the idea behind shadow mapping and you understand it from the OpenGL video, then on the Vulkan video, we're just going to focus on how to implement it with Vulkan. But we're not going to explain why you need the shadow map, how does it work, the shading, calculating the shading, the shadow factor is going to be on the OpenGL side, and then on the Vulkan side, we're going to assume that you know how to do it. And then it also helps me that I don't need to do everything from scratch, because it's a lot of work.
How much time do you devote to making these videos?
So it's usually on the weekends, and sometimes on weekdays, late evening. Okay. And yeah, that's most of. So I usually produce a video once every 2 or 3 weeks, and that's like the most that I can.
Okay. What was the impact of these videos for you?
I would say a lot, because basically I have a dream of simply working on the channel full time. Okay. Right now I cannot do it because it's not generating a lot of income or enough income from it, but that's kind of like the dream. So okay. Hopefully, I don't know, down the road or
okay, in the future.
In the future.
Okay. Nice. So what is there what's out there now in the future for the new videos, and what is out there for you on the Intel side?
So in terms of the videos, the plan is I'm kind of, because I don't have a lot of time and I always need to think strategically about it, because it's important for me to keep some cadence of some schedule, which is like not a video once every 2 months or 3 months. You can see some channels that do that, and they have like huge following, but each video is like, nuclear bomb. I mean, it's amazing what they can put there. But my videos are like more modest, and so I always try to do stuff which doesn't take a lot of research. I can kind of like I use a lot of books with a lot of prepared material, which helps me, and then hopefully with a few hours I can produce the video. And so right now it's kind of like becoming my comfort zone to focus on graphics, but I would like to expand into game programming and physics, which is often tied together. I mean, like collision detection. You can't really make any game without some form of collision detection. And this, I'm thinking about it. I'm looking at the books. I'm still haven't figured out when I can do it. But that is where I plan to expand in, like, not the near future, but the future that comes after, like in the intermediate future.
Okay.
Right now, I will continue producing all kinds of effects. You know, I have the physically based rendering. I'm working on SSAO, screen space ambient occlusion, Berlin noise for my terrain rendering. I think that there is already enough to create games with this information. It's enough. I mean, you can. I think it will be very nice to like read a book which explains game programming with OpenGL and have it produce some form of a simple game in each chapter, or even multiple times per chapter, just to show you what you can do with even the amount of information that you gain from this chapter. I don't think they do that. I have a few books on game programming that do that, but not on OpenGL, on older like 2D APIs.
Yeah, it's
It's easier.
Yeah.
Where you have a sprite and whatever, and then you create some silly game. So I would like to do that with OpenGL. Right now, I still haven't figured it out.
Okay. And on the Intel side?
So right now we're focusing, as I said, on deep learning. We're actually transitioning from CPU work to GPU work. Intel is also working on GPUs, not just for games like the one that they have released, but also for AI. And we are ramping up and start helping in the it's not the development of the GPU, but more on the performance analysis. So the idea, because my team is a software team, we don't have like architects or hardware designers. What we do is to analyze workloads and identify bottlenecks and performance optimizations, performance opportunities, and work with various parties within the organization to push them or to make changes to make AI work faster. That's the idea.
Okay. All right. Thank you.
You're welcome.
Etay. This was so cool. Okay. We spent 2 hours discussing the mostly graphics pipeline, rendering pipeline. Always wanted to do that on the show. Thank you so much.
Welcome. It was thanks for having me. It was a lot of fun.
Let's do the shout out to your channel, OGL Dev on YouTube. Where can people find you apart from YouTube? Where are you available?
So first of all, on the website. The website is not updated now with more content, but I usually just keep track of the video. So whenever a video comes out, I make a note of that on the channel, on the website. And if you want to read material on OpenGL, of course, you're welcome to do that. So that's ogldev.org. And I also have, I'm also available on TikTok. I have like a few videos on TikTok. It's not exactly TikTok material, and all the links are on the channel. Okay, to TikTok, and that's pretty much it. I have a LinkedIn account can be found by my name.
Okay. We'll put those links in the description.
Thanks a lot.
Thank you so much.
You're welcome.